Okay guys, in the last lesson I posed the challenge of combining radial and intrack burns and what is the end result of that. So as you might remember, I had these two ideas. One was a pure radial burn of 10 meters per second, and the other was a pure radial burn of 10 meters per second plus a 2.84 meters per second intrack burn, wait 24 hours, and then do a negative 2.84 meters per second intrack burn. I realized I didn't cover the other case, which is positive intrack burn 2.84 meters per second, and then negative intrack burn 2.84 meters per second 24 hours later. So let's just look at that really quick. So I've got a positive intrack burn 2.84. I wait 1 day or 24 hours, and then I do a negative 2.84 meters per second burn. So here we go. So the positive intrack burn raises my semi-major axis to this imaginary 78-kilometer line, and then the negative 2.84 meters per second burn lowers it back down to the geo belt. Energy in, energy out. Okay, taking it back to the radial burn. Okay, next is the pure radial burn, 10 meters per second. What is that going to look like? Sure enough, it's going to be an NMC. Haven't changed my semi-major axis. Okay, and now for the final prize. If I combine the 10 meters per second burn with a 2.84 meters per second intrack burn, so 10 radial, 2.84 intrack, wait 24 hours, and then I do a negative 2.84 meters per second burn, what's that going to produce? It's going to be this track here. Let's look at all three of them at the same time and see what conclusions we can make. Great, so you should be able to see that when I took the energy out of the combined burn, I essentially created the same NMC that the 10 meters per second radial burn created. So I essentially created an NMC and a drift at this point, and then when I got over to the 24-hour location, I took the drifting energy out, but I didn't take the NMC out. Hopefully this fundamentally helps you better understand when we say that these three axes of the brick frame are orthogonal to each other. You really can do a lot in one unit vector direction without impacting the other. So you can do this intract drifting burn and create this 24 hours of negative intract drift, and you can do a positive radial burn. But when you take the intract motion out, you're not going to influence the shape that was caused by the radial burn. Essentially, they are decoupled from each other. What I'm going to do in this lesson is help you better understand how you can combine intrack and radial burns to satisfy some different objectives. Okay, so for the first application of this concept, combining radial and intrack burns, let's just look at the classic Hohmann transfer. So as you probably recall from some lesson, a Hohmann transfer is the most efficient way to raise your orbital altitude from one circular or some eccentricity orbit to another orbit that is circular or some eccentricity. The classic Hohmann transfer usually deals with a circular to circular orbit with a transfer orbit in between. And the way a Hohmann transfer works is you raise your point of apogee, and when you reach that point of apogee, you burn again to circularize your orbit. So here I've built the classic Hohmann transfer to get onto this 78 kilometers positive geo orbit. So here we go, 12 hours, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I hit my apogee point, and now I'm going to burn again to raise my semi-major axis from this 39 kilometer point to 78 kilometers. Because I'm at apogee and I'm on that line already, this is going to raise my point of perigee, also 78 kilometers to this point. and I will now be in a circular orbit. And there you go, linear drift. Classic Hohmann transfer. Okay, but you're asking, what does this have to do with combining radial burns? I thought that's what we were going to talk about. Good point, good point. Okay, so here's the idea. What if waiting 12 hours to get into a linear drift is too long? Is there anything we can do to get into a linear drift faster? And the answer is yes. And I'm going to show you the application of that. Okay, so when we think about the fast transfer or Gaussian transfer or the transfer by many other names, really we're trying to lock ourselves into a singular idea. I want to get my satellite object onto this line of 78 kilometers, and then I want to take out all of my radial motion and set my semi-major axis to this 78 kilometer point. Sounds easy in theory, right? Well, here's one way we could do that. So I've created a new asset. I've created a new object that we're going to call intrack 1, and it's going to do a 2.84 meters per second burn. So fundamentally, I've already satisfied one of my criteria, which is I have my semi-major axis at 78 kilometers. So you go, you can see I've created a drifting NMC that is centered around the 78 kilometer point. And you can see at some point I cross 78 kilometers. Okay, so that's my other satisfied criterion met. I've got my semi-major axis at 78 kilometers, and I have my satellite object at 78 kilometers, right about there. So now I only need to satisfy my final criteria, which is I need to not have any radial motion at this point without changing my semi-major axis. So how can I do that? Well, there is a type of burn that can change my radial velocity without changing my semi-major axis, and of course that is the radial burn. And before I show you guys what this burn needs to be, first I want to show you one more thing with radial burns. So let's take it back to radial burns really quick. Okay, in the last lesson we talked about radial burns and how if I create a 10 meters per second positive radial burn and I want to stop that motion, when I get to the other side, I just do a 10 meters per second or whatever the opposite direction of my radial motion is, and I could take all that energy back out. So that's what you're seeing in this track here. I created a 10 meters per second positive radial motion. When I got to the other side of my NMC, that means I'm descending through the geo belt at 10 meters per second. And I'm going to take all of that energy out by doing another positive 10 meters per second burn. Okay, so let's take it back to our intrack fast transfer example. In this instance, I've added another line so we can see the NMC that we've created with our drift. And now we're going to try to apply two ideas together. We know that if I want to stop this radial motion, if this were just an NMC and forget about the drift, I need to do a negative radial burn because I'm traveling away from the Earth, which means I have positive radial velocity. So if I hit this point in this NMC and I do a negative radial burn, I can completely stop this radial motion as long as my negative radial burn is counter to my positive radial motion. So when we get back to this point earlier, when we're crossing the 78 kilometer point in the geo belt, I know that all I need to do is stop my radial motion and I can linearize this drift because I will have satisfied the requirement that I am at a semi-major axis point of 78 kilometers. My satellite is on that 78 kilometer line, and now all I have to do is stop my radial motion. So I'm going to go ahead and do that right now, and we'll see this happen. And then I want you to guess what the burn was. Okay, so here we go. I've got my 2.84 meters per second burn. I wait 6 hours, which is the point where I cross the 78 kilometer point, and then I do a negative radial burn. And sure enough, within the tolerance of perturbations, I have linearized my drift. Okay, so what was the radial burn here? Would it blow your mind to know that it was twice 2.84 meters per second, or 5.68 negative radial? 2.84 meters per second, wait 6 hours, and then perform a negative 5.68 meters per second burn. Maybe that doesn't blow your mind. Let's just take a look at the shape that is created by a 5.68 meters per second radial burn. As you can see, it's a 78 by 156 NMC, which also happens to be the same 78 by 156 NMC that's created around the 78 kilometer point when I do my 2.84 meters per second burn. So essentially, I'm just canceling this NMC out with the opposite NMC, a negative 5.68 meters per second, when I hit this 6-hour point. Okay, so there you have it. Using a combination of intrack and radial burns, I was able to linearize my drift in only 6 hours instead of waiting the 12 hours that a Hohmann transfer would have taken. The penalty for doing that, though, was an additional 5.68 meters per second over the Hohmann transfer method. So that's why Hohmann transfer is so efficient. And this is where we've lost some efficiencies. Now, what's interesting, at least to me, is it doesn't matter the order of operations that we do this. So let's say we do the radial burn first, 5.68 meters per second, and we create this NMC. As you know, from the geobelt to crossing the geobelt is going to be 12 hours, so we will hit our apogee point with the radial burn in 6 hours. Okay, so what if we were to do a 2.84 meters per second burn positive intrack when we're at this point of apogee? That will raise our semi-major axis to 78 kilometers above the geobelt, and our object will be at 78 kilometers above the geobelt. This should also linearize our drift. Okay, so here we are. We have 5.68 meters per second burn, creating that 78 by 156 kilometer NMC. We wait 6 hours, and then I'm going to do a 2.84 meters per second burn, lifting my semi-major axis to 78 kilometers. What's going to happen here? Linear drift. So this is the idea of a faster Gaussian transfer. You can use a radial burn to get your object to the 78 kilometer point faster, and then you can do a intrack burn to lower it. And you can apply this concept really any way you want. Here's a 11.36 positive radial meter per second burn, which gets to the 78 kilometer point after only 2 hours instead of waiting the full 6 hours it would have taken a burn that was half this magnitude. So now with this burn, I'm only going to wait 2 hours. And then I'm going to first focus on raising my semi-major axis to 78 kilometers above the geobelt. Okay, so now I've taken care of that. Now I just need to figure out approximately what is my radial velocity at this time. And it won't be exactly the opposite of this, because at this point, 2 hours into the burn, gravity has been pulling against the object, essentially slowing it down for us. So the radial burn that we're going to have to employ should be some factor less than this. This was the initial velocity that shot us away from the Earth, but now the Earth is pulling on this object. So I've just decided to estimate here that it's going to be about a negative 9.5 meters per second. Some value less than this, taking advantage of the fact that gravity is pulling on the object. If you really want to know what the exact value should be, then you can use, Newtonian physics, which is really true for all of this motion. But in this case, there's sort of a simple understanding of how much did gravity slow my object down in this first 2 hours to where I no longer need to burn as significant of a magnitude. So let's go ahead and take a look at this. So I've got 11.36 meters per second burn. I wait 2 hours, and then I'm going to set my semi-major axis to that line that I'm currently at, and try to take out as much radial motion as I can. And it looks like my guesstimate for the negative radial motion was pretty accurate. So now we've successfully completed a fast transfer that takes us from one circular orbit to another circular orbit in only 2 hours of transfer time. But as you can see, it's getting more and more expensive. In this instance, we've spent almost 20 meters per second total delta V. Actually call it 22, rounded up, rather than the original 5.68 that waiting the 12 hours of Hohmann transfer would have taken me. And now that we've unlocked our understanding of this concept, we can really start to get crazy. Like let's add a negative 2.84 meters per second burn, giving me greater drift with respect to the geobelt. So I'm going to move slightly negative intrack for the first 6 hours, if you remember from our drifting case. And I've got this positive radial motion. So let's see if this, first of all, will cross our 78 kilometer point. And indeed, it looks like it does, before going on to its eastward drift, since we've lowered our semi-major axis. But because that apparent motion, that apparent west to east motion, doesn't start to come into account for this negative intrack burn until after the first 6 hours, we've taken advantage of the fact that we're still moving to the west. So now let's get to this point here, which appears to be about 30 minutes after the pure positive 11.36 meter per second burn. Now let's see if we can linearize this drift. Okay, so here it is. We got 11.36 meters per second positive radial and a negative 2.84 negative intrack that is taking us from a higher semi-major axis to a lower semi-major axis, but we're trying to take advantage of this originally westward motion. It looks like about 2.5 hours is where we cross the geobelt. So now what we need to do is raise our semi-major axis to 78 kilometers above the geobelt, which, because we first lowered it 78 kilometers, we're now going to have to raise it to geo and then add another 2.84 to raise it to 78 kilometers above that. So that'll be 5.68. And we also need to take out all of our positive radial motion. Which, just on an eyeball test, looks slightly less than the original radial burn. So I'm going to guess a -8 on this one. You can see I way overestimated the amount of negative radial that I needed, so let's just dial that back. So we'll try out about a 5.5. And that looks not bad within a certain level of tolerance. Okay, so what's the benefit of that? We still have been able to move from a circular orbit to another circular orbit in way less than a Hohmann transfer. And not only that, but we are now ahead of the object that just started out with a pure radial burn and then linearized at this point here. So because we started with a negative intrack motion, we've been able to take advantage of the fact that we're now further along in our westward drift. And interestingly enough, it actually required less delta V for us to get to this point with linear drift than it did for us to get to this point with linear drift. As you can see, the total magnitude of our burns was around 12 for the first burn and 8 for the second burn. versus 11.36 for the first burn, and then about 10 for the second burn. Okay, so that's just kind of a quick tack teach on how you can start to combine these directional burns into something more meaningful. Really, the understanding that I think enables this level of problem solving, even just with a basic calculator and no, differential corrector tools, is just these are just shapes, NMCs. Really, everything is a drifting NMC of some sort. And if you start to understand that there are ways to impact your NMC based on the time that you are in with respect to positive or negative radial motion, and there are ways to impact your east-west drift with respect to your semi-major axis and intrack motion, if you start to unpack those and create them as separate concepts, then when you can repackage them into a more fundamental understanding of just your velocity of motion and your apparent motion with respect to some frame of reference.